All right. So data munging with Python, and let me show you. We'll start with the. I'm sorry. Was somebody saying something, Conrad?
No, you're good. Sorry about that.
All right. Okay. All right. So yeah. So this basically started with me trying to figure out what is happening, right? I mean, how are so many new things coming up, and how can I get a handle around this thing, right? So I started basically building this as kind of notes to self, and it grew from there because lots and lots of people then came up to me and started showing interest, and that was kind of cool, right? So um, let me start today's presentation really quickly. Um, that's PyData Global. And here we go. Right. So no idea why this is not Rise, working as Rise. Well, we'll just take it from here. So, oh, by the way, for these images, I right after I presented this in PyCon India, I got DALI 3 got released, and I started playing with that, and I just went nuts. So I apologize. The entire workshop is now littered with these images, but yeah, what if we found Greeks doing data munging with Pythons, right? That would be a fresco. Anyways, so quite often we see that uh, we have these variety of technologies just coming up and going. What am I trying to do? And we getting overwhelmed with, hey, these new things are coming up again and again, and how do we get a handle on that, right? um, so this workshop is me trying to answer that question first for myself, but hopefully for a lot of us around here, right? um, Let me start quickly with my introduction. I have 20 plus years of experience everywhere. um, and I consistently hear text changing so fast. It's hard to keep up. And I'm sure you hear that too, right? Um, so if you're looking for me after the presentation, you can find me on LinkedIn, Facebook, Instagram, whatever, right? I work at Barnes and Noble, and I'm very happy to report that I'm very, very lucky to have run into a really good team. Um, the idea of a good team is that we treat each other as experts. We don't tell each other how to do our jobs, and we keep each other on our toes, right? I have to learn if I have to manage that team, and the team has to learn if they have to live with me. So it's a really good symbiotic relationship, and I'm very lucky. It doesn't happen quite often. Um, Additionally, I write plays and screenplays and work in films on the side as well. And I got to shoot and produce this movie about a year ago. Right, it was released here in India. To quite some fanfare. Right, so yeah, so legit Bollywood experience in addition to Python. Um, so yeah, so let me run this. That's how you run a video in a tied Jupyter notebook. So needless to say, I really, really like films. And hence, I hope it justifies my inclination towards using the movie lens dataset. That and the fact that it's really easy to understand, right? So let me just show you quickly what the movie lens dataset looks like. Um, Typically, we will be using two data sets from here. One is the ML25 million data set, and the other, if you scroll all the way down, you'll see the educational purposes data set. Education and development, and we'll be using this latest small data set, right? I will be using it locally. So on my local machine, I have this already downloaded. Um, and yeah, so this one as well. Um, and interestingly enough, this when you unzip this, this is about 1 GB of everything, right? So quickly, let me show you this bit. Um, um, Basically, we're looking at movies, their ratings, the links to these movies to IMDb and other websites, and the tags that users have associated with these movies, right? So just four different entities, not complex at all. The README file explains how the data set is laid out, right? So you can download and explore this data set yourself, or just go along with the workshop and it should be fine. Um, I tried my best to put in the links to, so if I go to the workshop, let me go to the PyData global folder, to put links to Colab, right? These may be slightly messy or may not be working for some situations. Let me know. And we can update this in real time. But for the most part, at least till yesterday, these were working fine, right? So you should be able to, without wasting time on too much time on setup, be able to click on Colab for any of these and then follow along. I am going to request, Conrad, that you speak up if somebody's asking any questions or raising hands or whatever, because I can't see. I'm working on a different window, so I may not be able to see what's going on. Does that make sense? Is that okay?
Okay, perfect. So we also have Desmond with us, and we will be monitoring the chat and also the Q&A. And we will show it on the screen and also verbally notify you if there's any questions.
Perfect. Perfect. Yes. So the GitHub link. Let me first share the repo link with everybody, because I've been just harping around, but did not share that. So let me do that first. There we go. And let me know if you can access the GitHub repo. Should not be a big issue. All right. So So let's get back to that tech changes so fast bit. I'll speak for maybe 5 more minutes, and that will give everybody a chance to download the Git repo or clone it or fork it or whatever you like, right? So, and then we'll also look at the Git repo separately, right? Is the font size enough, or should I increase it more? Let me increase it more, anyways. Hopefully this works. I don't know. All right. Um, okay. So in addition to the movie, I got to collaborate on a play called The Little Prince. I hope a lot of you have heard about this play, this book, um, and one of my favorite books. And one quote that I came across in this book was, "If you want to build a ship, don't drum up people to collect wood. Don't assign them tasks, but rather teach them to long for the endless immensity of the sea." I'll say that again: teach them to long for the endless immensity of the sea. And this tutorial is basically my attempt at doing that, right? So when we look at technology and we say, oh, there's pandas, and now there's Arrow, and now there's yet another technology called Velox that has come out of Meta. And how many do we learn and how do we keep up? That statement becomes problematic because it's overwhelming and we don't know how to solve it. But if we like the field of data engineering, if we like the data itself, and if you're curious about how what that data has to offer, everything else becomes like a ship that you'll be sailing on the sea. So I try to divide everything into a sea question or a ship question. And ship questions take a lower priority, right? They can be solved, right? There's Google, there's ChatGPT, there's Bard, which is surprisingly good now. And there's tons of other things now helping us, right? So there's PyData. So effectively, the focus has to be on the sea. We have to learn to love the sea, right? And the ship then becomes the easy part. So so that's my motivation for the workshop. The approach we'll take is we'll start with just plain Python, right? And I'll spend a good chunk of time working on Python because all I want to do is, just lay all the concepts clearly, and that should give us enough grounding to be able to cover Panda, Spark, and anything else like really, really quickly. And you will see yourself as we go through the exercises that you're able to just kind of handle it really easily, right? So we will focus, and it's entertaining. It's not boring, I promise, right? So um, we'll start simple and then build on top of it to the point. My expectation or my hope is that at the end of these 2 hours, you will be able to tackle any of these data engines or upcoming ones on your own, right? Um, so, so we'll cover, like I said, the core Python collections, and then we'll see how NumPy does better than Python and where it does better. And then how Pandas builds on top of NumPy, and then how Spark comes into the picture, and why is there a Dask if there's already a Spark, and what does Polars do if time permits? We have a lot to do, right? So quickly, um, if we run this workshop properly, like with every single notebook and everything, it becomes like a 5-day event. We only have 2 hours, right? So we'll not be able to cover things like func tools, iter tools, time series or categorical data, and things like that, right? So there's a lot of questions, and what I've done is I've built hopefully enough in the workshop that you can continue to grow with this one, right? So please interact. There's discussions enabled on the GitHub repo. So you can go to the discussions tab and start asking questions. A really good thing about a workshop like this is that there really are no dumb questions. When we are very new, very fresh to something, we bring our own perspective and we actually ask surprisingly deep questions. So it's really, really interesting to capture all the questions and sort of build a knowledge base that's really practical and community generated, right? So ask your questions in the discussion. If I can't get to them in the talk, we will definitely touch upon them. Um, I will definitely answer all of them here. There was somebody who actually wrote a question as an issue, and yeah, so we had to then I answered that here as well, right? So prefer discussions, or whatever's easy and convenient for you. All right, here we go. So let me quickly first give you a walkthrough of the GitHub repo. All right, learn data munging. For every data engine, I've created a separate folder, and it's growing. You can see that Data Fusion is already there. Ray is already there. I'm not seeing too many updates in Ballista though, so maybe it's just going to be Arrow and Data Fusion. And there's tons of other data engines. So what I'll do is I'll keep adding as I explore more and more and more, right? There's sidebars, which were basically things that I ran into or questions that was asked, which were not exactly related to data engineering, but like kind of general enablement questions. For example, how do you put in that open and collab button and things like that? So I just made sure that even that is available everywhere. There's archived, which is just a trash miscellaneous drawer. I should have removed this. This is an error. And then on the README page, what I've done is, in addition to all the notebooks and everything, I've put in all the references that helped me learn, right? So everything is transparently available. you can say, hey, here's a good resource that I want to use, and you can submit a pull request for that, right? Um, my hope is that this is the most updated reference that I have, and a lot of these would be kind of really, really old. You can see some links from like 2014 here. Um, but these were all super interesting. And if I can urge you to do one course, that's the Advanced Database Systems session from CMU. But okay, let's get back to the repo. And all the work that we will have to refer to is in the PyData Global, right? So if you go here, you can see the links to the notebooks that we will be running today, right? Please post a message. Please raise a voice. If you want me to slow down or if you've missed something, we'll happily cover it, right? So let's invert the pyramid really quickly. Here's the 6 things that I typically ask when I'm choosing the right ship for my voyage, right? My focus is the sea. So for any ship that I choose, I ask whether it is going to have lazy evaluation or eager evaluation, right, of expressions, whether it supports only scalar operations or whether it can support vectorized operations. How does it represent the data in memory, right? Row-wise and column-wise, row-wise or column-wise. And column-wise is typically also used these days. It's called columnar, right? So we see a lot of these vector databases coming up they're saying columnar. So we'll see what that really means here, right? How is it represented on disk? On disk, you would have heard of things like Parquet and Avro and things like that, and why are they important? And then what are the task scheduling features available? What sort of optimization considerations are there? And how poly does the ecosystem get, right? So for example, in Spark, you're looking at Java, you're looking at Scala, and you're looking at Python, right? In Arrow, you're looking at Rust and you're looking at Python. But so operationally, when you want to push this to production, how hard does it get? So those are the considerations that I typically look for. But my focus is always on the data and what it's teaching me, right? So let's quickly look at the Python thing first, right? Python does eager evaluation. As soon as it's given a command, hey, find the average of the following numbers, it just executes it, right? It's really good because the results are like available now, right? But for larger data sets, we may want to filter the data set first, right? What's called the predicate pushdown. Predicate pushdown, right? That's the fundamental optimization technique available in practically every data engine, every database, right? So things like that. If you want to filter a part of the data before running your compute, eager evaluation doesn't let you do that. That's the problem. The second thing with Python is that its data representation in memory is kind of expensive when you think about just structured tabular data, right? But it's beautifully done. It's because of duck typing, right? You don't really have to worry about types and type safety and stuff like that. If it quacks like ducks, if it walks like a duck, it is a duck, right? Python figures it out for you. So the way this works is that if you look at a table that's got all the headers, right? So the movie ID, title, and genres, then each of these are stored in different locations and that are not contiguous, right? So the analogy that I typically make is imagine an apartment complex, right? Each of these is one of the apartments, right? So what the computer has to do, what the data processing engine has to do is go to each apartment and fetch the value, and then go to the next one and fetch the value. And these may not be right next to each other, right? So this is apartment 3, this is apartment 7. So the time spent in seeking the next value is significant, right? And it grows as your data volumes grow. Python is not going to put it in contiguous chunks. These are dynamic arrays, so they provide a lot of flexibility, a lot of functionality, and they're really, really fun to use. But they don't handle gigabytes of data, right? So let's switch to the Python notebook and see what we have in store, right? So we'll go here, and so I have deliberately kept the func tools, iter tools, and practice questions empty for now. I think I went nuts and like put images everywhere, but beyond that, it's all empty, um, because I wanted to keep my focus on this notebook. All right. Um, so again, support for Google Colab. When you open this in Colab, I need you to uncomment this. That's control and / uncomment this and run it. Okay. Ideally, it should download the data and set things up for you just fine. And please let me know if that doesn't happen. All right. Um, in fact, if you run into any kind of special fun problem, do put it up in a discussion, so I can research it and document like a proper generalized solution for it, right? Um, we will use the small movie lens data set here. And the first thing that I'll do is open it up and try to understand what it looks like and how it works, right? I'm deliberately not opening it up in Excel or anywhere else, because let's only use Python like we would in a real world situation, right? Or let's challenge ourselves to use only Python. So what I'll do is I'll start running these cells, and I would very much appreciate it if most of you can run it alongside and tell me if you're seeing what I'm seeing as well. And I'll explain the code cell by cell as we move along. All right. So we're just basically first setting up these global variables. Where's my data located? And I'm creating these variables, which I will use forever to refer to the movies file or the links file or the ratings file or the tags file, right? So like we saw in the data folder, there's the latest small. So we're using the small data set, right? It unzips to about 3.5 megabytes, which is trivial. Should be able to work on a computer, right? So remember we had these 4 files, right? And so what we're doing effectively is we're just saying, hey, where are these files located? So let's just see what's inside a file, right? So this is the very old school. You have a text file. Show me the first n lines, right? I can just there we go. There's a bug in here. So this should be like this, right? And that is it, right? So if I run this, I should see the first, whatever, 5 lines, right? So when I run this, I see that my movies file has a movie ID, a title, and a genre. Well, it's genres because all the genres are clubbed together. And I absolutely love these things, because then this is like another interesting problem for us to solve. And we don't have to like think about, oh, this is bad data. No, this is a lot of data actually gets created this way. So it's pretty interesting if you want to do some analysis now that around the genres, how you will actually unpack this thing. I can do a render lines and say 12, and I should actually see what happened. Did I do something wrong? Oh, I should say no lines equals 12. I'm nervous, guys. PyData is a big deal, right? All right, so we see 12 of these. And here's an interesting case, the American president. So do you see how there's like a 4th comma here? So if I was to unpack this, I'll have to wrestle with this 4th comma somehow. So if I was to just read the CSV, yeah, this is going to be interesting, right? So this, I'm just explaining to everybody what the file looks like. Um, but the first question we should think about when we get some data is, hey, are there headers or are there no headers, right? And it's not a good thing or a bad thing, but they have their own processes, right? If there were no headers, I will need a guarantee that the first column's always movie ID, the second one's always title, and the third one's always genres. If there are headers, then from one file to the next, the column order can shuffle. Let's say there's an asynchronous process that's actually collecting this data. Imagine processing log files, or imagine processing different kind of sources, same kind of data from different sources. Let's say the sales file from 3 different banks or something like that, right? So if you have headers, you don't need guarantees for position. If you don't have headers, you need a guarantee for position. So that's kind of the first thing we think about. Um, we can test this for other files as well if you want, right? Let me know if you're facing any problems here. We see that for the links file, we have the movie ID, which is the same as the movie ID here. And then there's an ID here that'll allow you to generate the URL for its IMDb page or the TMDB page, right? Similarly, for tags, we can see the movie ID and the user ID and the tag that the user gave, along with the timestamp when the tag was given. Timestamps are fun, right? Date time, always the most fun bit of any kind of data analysis. And finally, there's the ratings part. We're expecting the same thing, right? A user, a movie, what rating the user gave, when did the rating appear, right? So we're looking at the same thing, right? A user ID, movie ID, rating, and timestamp. So when you think about it, that's it. That's the entire movie lens data set. Super easy to understand. I'm going to switch back to the AirMeet window, see if there's any questions right now. Okay, there's like huge. Anna says you're testing our debugging skills. Yes, please. Thank you. Yeah. All right. So let's actually get to something more useful than just looking at the data, right? So what I've done is I've tried to articulate what we will do as problems, right? You can just listen to me, but you have the repo. You can try to solve these problems yourselves. And then we can compare notes. And you can say, hey, there was a better way of doing this, right? And yeah, my secret ambition is to actually learn from this session more than I give, right? So help me do that. So Python by default provides these 3 data tools. A very interesting thing that happened very recently was somebody said, hey, I need to prepare for my interview, and can you help me with Python? And the first question I asked him was, hey, are there arrays in Python? And surprisingly, the gentleman didn't know. And Python doesn't have what we traditionally know as arrays, right? Python has lists and tuples and dictionaries, and they're fantastic. All right. On top of these, Python then builds a collections module that provides additional features, and we'll see how interesting things can get only just using Python and nothing else, right? So let's think about some of the questions we'll ask our data, right? We did this raw file extraction, right? But is there a way for me to extract 5 titles from the start of the movies file and 5 from the end of the file? Just so I can see that, okay, it's got nothing that's corrupt, right? I can basically touch any part of the file and it returns something sensible, right? The second, how much, how many, how big? That's a quote from Little Prince. How much does it cost for me to process this data? How many lines are there, right? How big is the data, right? Can we get the different markers of size and cost for the data? That's really interesting. There is a new, well, not new, but there's this growing movement of FinOps where we want to be able to say, hey, what will it cost me to build a certain model or to do X kind of evaluations? And so if we have these markers up front available, it becomes really easy to calculate that downstream, especially for cloud-like environments. If nothing else, it will actually tell you the time cost of your computations, right? Well, can we do some database style access? This is pure Python, remember. We do not have an RDBMS with us. So can we like do a select star from movies where movie ID is 206? I don't know, let's try. What's the frequency of each reading? That's a really interesting question, right? How many times was the rating 1 given in the entire data? How many times was the rating 2 given to a variety of movies at variety of times by a variety of users in the data? So if the data has a lot of 5s, we know that it's skewed towards lenient ratings. If the data has a skew towards 1, we know that it's really, really harsh. So this will help us see where the needle's going and evaluate how fair these ratings are, how unbiased we can take these as when we're building, let's say, a recommendation engine. Is there a way for us to find out the average rating on the movies based on its movie ID? That's a typo. I have no idea why. Oh, IE space. Apparently, I don't know how to use a keyboard. I'm learning, guys, right? Okay, and finally, can we find out the number of movies in each genre? So remember this really packed field. Can we unpack this? Come on, that's an interesting problem, right? How many adventure movies are there? How many romance movies are there, and so on, right? Seriously simple questions, really interesting ways to find this out. Let's crack each one of them in turn, right? Before I begin, again, quick check on the air meet bit. Am I speaking in the void? Oh, there's people here. All right. Okay, here we go. Let's get to the lists, right? So really simple stuff, okay? There is this notion of list comprehensions, and and these are basic Python concepts. I hope all of us are aware of these. If these are not clear to you, let me know. I'll explain these really quickly. But lists fundamentally are ordered sequences of elements. The word elements is important. It is not, lists do not insist that you have everything of the same type within it, right? Duck typing, right? Python, as it's traversing through the list, can figure out what type of element it is, right? And lists are mutable. You can actually change the values in a list very easily. So we create a movie titles comprehension. Well, spoiler alert, we have a really interesting section on list comprehensions in this notebook, and I'll skip it. Let's have kind of a poll if you want to get into nested list comprehensions in this notebook. It'll add maybe 5 minutes to our overall presentation. So let's look at movie titles. What we're basically saying is that for each line in the file that I open, right, I want you to split that line using a comma and just pick up the second field. So we have zero-based arrays, pick up the second field. Seriously simple code. Can anybody tell me why there's a 1 here? I'll switch to the chat. Somebody tell me why there's a 1 here. Yes, thank you. Awesome. So yes, because we want to ignore the first line we saw where we have the column headers. That makes no sense, right? We're looking for this line. That's the data. So like I said, our files have headers, and this would have been a really minor detail, really easy to miss. And all hell would have broken loose when you ship this code to production. Right? So let's run this. And what we see is that the first 5 movies here, I really like the style that Python provides. So we're saying from the start of the list till the 5th record, till the index is at number 5. You give me that. And the minus says from the last count 5 and give me all of them, right? And this missing thing is, well, it's the last one, right? So look at what we just did. We basically could read any part of this thing, right? So I can just say print, and let me add a new line so there's some space, dot join, and I can say movie titles and give me 2 numbers, 200 to 207. Right? Pretty cool. So I can access any random part of this. I really should say random. Do you see random access somewhere? Man, I should have worn my glasses. Oh, there we go. So yeah, we can actually pick movies from any part of the file. So looks like we have a good file. Yeah. So quick poll. Do you want to get into nested list comprehensions? You know what? I will skip this for now, right? And if enough people say we want to talk about nested list comprehensions, we'll come back here, right? I just want to show you one line here. That's really precious. That's amazing to read. And this is genre for genre, in genres for genre, in genre. Come on, this is precious. This code, if you put, I promise you the next engineer who reads it is going to curse you. It's going to hate you so much, right? So list comprehensions do make me feel really dumb sometimes. So they're kind of cool, but they have a people problem. All right, how much, how many, how big? Let's look at all the methods available for movie titles. Remember, we just created a list called movie titles, right? So let's look at all the movie title methods available and look at the methods available for each element of that. So lists don't need to have all the elements of the same type, but in our case, we know that all the elements are of the same type, right? So let's look at both and then also see the type of that element. So I'm going to run this. And now if we print this, this is very interesting. So look at the 48 methods that each list supports, right? Each time you create a list, right, that movie titles internally has 48 instances, 48 method instances, right? So you can add to it. It defines the class. It gives you a way to check the contains. It gives you a way to assess equality, greater than, less than, hash, and so on and so forth. And it does give additional functions like you can append to the list, You can extend to the list. It's very interesting, the difference between append and extend. Hopefully we covered that in this notebook. We can see that all these features are available out of the box for a list. This is very similar to the array interface that we see in JavaScript many a times, right? So really interesting for me to see this available. Try doing that in Java without creating an iterator class, right? So yeah, this is quite awesome. But here's the kicker: for each element in the list, we have similarly so many methods, because it can be any type. So duck typing means we have to support a general purpose functionality, right? So every record in the movie's data file has 81 methods and 48 methods for the overall list, right? So that's interesting, right? Um, so, spoiler alert, that's one of the optimizations that NumPy will build upon. So, the insight there was that if you're doing a general purpose data analysis, we can actually restrict the duck typing thing, right? So, we can say, oh, we only need strings in this column, or we only need integers in this column. And we can start paying attention to data types, and maybe that gives us some optimization. And we'll see what kind of optimization there is, right? So what we'll do is, before we tackle other kinds of data structures, let's quickly build a helper method. I'm not going to go through the code here. It's really, really simple. We're still getting the same dir for all the methods and size and so on and so forth, right? So really simple stuff. And here's testing this method. So if I create a integer, it has 73 methods. If I create a float, it has 59 methods. If I create a string, we just created one, 81 methods, and so on. So kind of works, right? I wonder if there's a way to create a general purpose message that also general purpose function that also handles things like pandas data frames and Spark data frames and so on. But for now, like, this is good enough, right? So now let's get back to the regularly scheduled programming. That's kind of an old-timey radio thing. I don't know if anybody. There have been people who ask me, what does that mean actually? Why do you say that? So I'm old. So tuples, right? Same kind of thing, except that these are pairs of information that go together, right? So you can now start thinking about tables in an RDBMS, where you can say, or like things like coordinates in computer graphics, right? So you can basically start binding information together, and they travel together, right? So I want to say, hey, what are all the movies and just the genre pairs? I don't really care about the movie IDs or anything else. Just help me create these ones, right? So again, we're doing the same thing. We're using list comprehensions, and this is a list of tuples, right? So tuples are indicated with the brackets, right? And we're saying create a tuple where the first value is the movie title and the second value is the list of the genres, right? And that's it. It's kind of the same code. One means headers are there, right? So we suddenly have a way of looking at two things together, and that's added information. But you see this R and N. I'm looking for suggestions from folks at the call how to remove that. We're going to remove that in a future event. But right now, here's an interesting exercise. Right now, how many of us can actually remove this part? And then when we look at the overhead for the tuples, like we saw, 48 methods for that class, so many records covering so many levels of depth, occupying so much memory in the system. Remember, the movies file by default is just about 43 kilobytes, right?
Hi,
So
sorry,
40 kilobytes blooms to two.
sorry, Agal. Let me interject? There's a question for you.
Sure.
Uh, yeah, does type annotation feature can be used to limit the performance implications due to Python's dynamic language feature, or are there other ways to do this?
I apologize. Do you mind saying that again? I didn't hear that.
Yeah,
Sorry.
so it's in the chat session. The
Right?
first does type annotation. No, scroll down a little bit. Yep,
Type
does type.
annotations can be used to limit the performance implications. Oh, yes. So yes and no. Depends upon the kind of operations we're trying to perform, right? And we'll cover that. So we'll not specifically cover type annotations, but we'll cover, so the typing module itself, I want to handle separately in a different notebook. But we will cover how to tackle this overhead here. So stay tuned. But great question, by the way. So again, we saw the overhead, and we're looking at something that blooms into 2 MB almost. Um, just and we actually shaved information away. We actually rejected one of the columns in the data that was available to us, and still it's covering this much. So that's kind of the overhead we're looking at. I know that I'm making it sound like it's a really bad thing to have this overhead. It's fun. It's amazing when we're doing application programming or when we're doing like some quick and dirty stuff. But it becomes a problem when we're handling larger volumes of data. Um, the same thing I've covered for the individual parts of the tuples, right? So each tuple covers 35 methods. It's got a length of two, because it's got the movie title and the genres, right? And it covers 3 levels of depth. Anybody tell me what these 3 levels are? A tuple has 2 things. So what's the third level? Come on, this is really easy. Let me know. It's the tuple itself. So the data structure itself and the things inside it, right? Um, and this is the individual elements, and those are strings, right? So we know that's 81 methods. So imagine when all of this gets nested, you end up with 29,000 methods available in your memory doing nothing at all. Why? Because eager evaluation. We just evaluated everything, so Python just filled up the memory. So eager evaluation is a interesting beast. It helps you keep everything ready now, but it also limits how much you can scale, right? Um, and let's look at dictionaries really quickly. I want to just move on from here. The same thing happening here. We just created a dictionary. Let me just show you quickly. Um, where did I go? Let me do this. Actually, there's a better idea. Dictionaries. All right. Um, So what we're doing here is that we're splitting the data with the comma, and we're saying movie ID and title. And that should give you a hint to what's going to happen, right? I'm going to create a key in the dictionary that's the movie ID and assign it the title, right? So same, I can list the first 5, I can list the last 5, works just fine. But this is the first one, right? We can now access, just like in RDBMS, we can say, what's movie ID 260, right? And that's, well, Star Wars. Hopefully, some of us have seen that movie. It's like an art film from back in the day. Um, and we have 9,742 movies in our data set. And here's the overhead, right? We're looking at about 1,300 or 1,400 kilobytes in the memory. Um, Again, we actually removed the genres column, which is probably the largest column there is. And we still ended up with 1,398 KB, right? Um, And then finally, there's sets. Sets are interesting. Set actually evaluate uniqueness each time you add something into them. Sets, just like the mathematical concept, don't allow for duplicates. That's awesome because now I can just push stuff into sets and say I know everything's unique inside, right? So So what I'm doing here is trying to load all the genres, I'm sorry, right? I'm trying to identify what are all the genres in my data set. Because remember, if we go back up, oh my God, I'm gonna have to scroll again. Can you see how romance happens multiple times? Comedy happens multiple times. So if I just let the genres be, I'll not get the unique set. So what I'm doing here is trying to print all the unique genres, and this is where our extra comma plays truant, because we now have these parts of the movie title actually appearing as genres. That's a problem, right? So reading CSV data is a very interesting problem in itself, which we'll cover in a separate notebook, because I want to cover building a parser for raw Python, for Apache Spark, for Dask separately, right? So we'll build a separate notebook around that. But for now, let's just try again, okay? What I'm going to do is I'm going to call strip and split, right? And I'm going to now look at the last entry in my row data and say split that by a pipe, right? So it doesn't matter if my line has 4 entries or 3 because of the comma, extra comma, I just pick up the last one. And effectively, that gets us all the genres in each record, and we just keep pushing that into the set, and well, immediately we get all the unique genres. So simple. So if you had this bit, which is all the genres with the duplicates, right? Once you've had this, it's trivial to turn it into a set, except there's processing cost associated with it. So we'll look at it, right? So the moment I do that, that's the unique genres that we find, right? So here we have all the genres that is there in the data. Interestingly, I think there's no genres listed as well. That's pretty cool. Some films don't have a genre. Pretty awesome, right? So there's inherently some null values available in the genre data, which means we'll have to be careful if we're trying to create cohorts or buckets based on genres. Let's look at the overheads, right? Yeah, not bad. But let's think about, and I think I'm doing that somewhere down the I don't know where I did it, but later in the notebook, we'll actually calculate the cost for these, right? So, am I doing that here itself? Oh yeah, there we go. So to calculate the cost, what does a uniqueness check take? It will have to parse the list once, right? For one uniqueness. The second one, parse it again. Third one, parse it again, and so on. So worst case scenario, we have a big O n squared complexity here, right? In our specific case, if we just wanted to calculate the number of operations, it will be the number of genre, a number of elements in genres with duplicates list, and the number of total unique genres found, right? So that's, oh my God, that's like 441,000 operations. Yeah, that can be expensive, right? So yeah, sets are really cool. They're kind of expensive, but if you were to write that code yourself, and everybody has to write a distinct, right? Everybody's written an SQL statement with distinct, right? So yeah, they're expensive, and we have a measure of how expensive they are, but they're really interesting, and thank God they're available out of the box. So let's look at some of the features available in the collections module, and then quickly move on to the NumPy notebook.
So sorry, before you go ahead, there is another question.
Sure.
The last chat, yes.
Yes, this is. Thank you. I'm sorry, I don't know how to pronounce your name, Ade. Thank you for the question. I'm covering that in a few minutes, right? Um, right. So let's look at the named tuple. Named tuple is basically just expressing the schema or the equivalent of a schema. Of course, being Python, there's more than one ways of expressing a schema. But named tuple is one of the simplest ones, right? So we can say, hey, my movie is a named tuple. My movie class is named tuple. And it's got 3 columns. It's got a genre, a title, and a rating, right? And I can just create a variable, put a movie in it, and I should be able to access these individual values using the dot notation, right? So you can see that I'm taking that variable and just saying dot title. So I can just literally create values here. And again, oh, did I not? Thank God. So all I'm doing is inputting values, and you can see duck typing happening here because we have strings and we have a float, right? So we didn't actually express, hey, my rating is a float. It picks it on its own. Um, Similarly, I can say here's a named tuple for a rating. And like we discovered before, it's got a user, it's got a movie, the rating the user gave to the movie, and when the rating was given, right? And very simply, I can actually create all the ratings as a named tuple from the ratings file. And now I can just play with the ratings. Um, I've not tested if rating is coming in as a string or not. My intuition says rating is a string. In this case, we'll have to convert it ourselves. So the interesting bit here is the star, right? So what this line is going to do is it's going to generate one or more arguments that will go into the rating function, right? Which will generate a named tuple for us, right? So the star basically says one or more positional arguments. The double star says keyword arguments, right? And you can just pass this as an array. A lot of people I meet have been forever confused with it, so I just put a link here. Not that hard, just look at it, right? So that I can now randomly check ratings for individual movies. There we go. And now I can look at the overheads. And we're looking at about 6 megabytes in the memory. that's, and if you look at how complex name tuples are as compared to plain old lists, because when you think about it, just a list, right? Where did I go? There we go. So if I just run that, we're looking at, it's approximately 5 times in our case. Makes sense, right? 4 extra fields. So yeah, more expensive, but certainly convenient. Now, I don't know how to pronounce that. I pronounce it DQ because that makes sense to me, double-ended Q. But a lot of people I know pronounce it like deck. So please comment and say how you pronounce it. It's like a GIF thing that I keep running into. I'll say DQ at least for this presentation, right? From collections, we again import, and we basically build a DQ where it's in the name, right? It's a double-ended queue, and when you look at the implementation, it's super simple. We're adding elements, and we're saying it cannot have more than 5 elements. So the queue starts popping individual elements off as it keeps adding elements on the right. Super simple, right? Overheads, I'll just run it. I don't think it's important right now. Counters, very interesting. Counter is effectively the dot count aggregator that we find in multiple places, right? So that's available out of the box in a language. That's just, I've not seen that in JavaScript. I've not seen that in Java. I've not seen that in C++, certainly. So this is kind of interesting that a language just says, hey, I'll give you batteries included. All right. Same, we have an arbitrary list of genres. I'm going to say, hey, count each of these occurrences, right? So this is kind of a group by dot count happening, right? And remember how we created the genres with duplicates right at the top? If I just give it to a counter, it's going to tell me how many drama movies we have, how many comedy movies we have, how many thrillers. And that was one of the questions we were trying to answer at the top, right? So did any of you get here before I did? Because I'm wasting too much time. Okay. Also, I have not covered the name tuples versus dictionaries just yet, right? So let's now talk about a slightly more complex idea. Count the frequency of each rating. It's not hard. Remember, we've actually done all of this, right? So let's just try it once. So name tuple counter, let's import them again. We're saying, hey, rating is a name tuple. We've defined it upstairs as well. Let's just do it again. Remember the asterisk here. It just says positional arguments, one or more found. And that's it. And we're doing the one because we're skipping the header, right? And that's it. We have a list of ratings. I love dictionary comprehension. List comprehensions. Oh my God. Look at the precious line of code here. I don't know. You can actually kind of like put this on a t-shirt and say, read it if you dare, right? Don Knuth, I like that gentleman a lot. He came up with this idea of literate programming, where you can just read code as if you were reading a novel, right? And I think all the discussions around object-oriented or functional, they actually distract us from the literate programming thing. And the pure Python is closest we've gotten there at scale. But again, we have list comprehension, so yeah, limitations to everything. But yeah, there we go. We suddenly have a list of ratings, and we know that there's 26,800 movies that have a 4.0 rating, 5,500 movies, that's about 5 in the rating, and there's so many movies that actually have a 2.5. I'd love to dig deeper into this one. And so we can now see the most common ratings. We can see the least common ones and so on, right? Super easy. Again, kind of overheads is a theme on this notebook, right? So let's just keep looking at it. That number blew my mind. Just to calculate that ratings, we had like 28 megabytes. What? And the ratings file itself is like 2 megabytes, 2.5 megabytes. So yeah, interesting. Finally, we have the ordered dictionaries by default do not guarantee the order of their keys. They use hashes, right? So they're all the keys are basically hashed inside a dictionary, so you can't guarantee order. Ordered dict does, which obviously means it's slower than a regular dictionary. So we're adding movies in an ordered dict in order, and you will be able to get them out in the same order, right? So fairly simple. What is the average rating of a movie in the ratings file? Average rating. So let's say we look at Inception. What is the average rating of Inception? Now you think about it, it's the ordered dict really works here, right? So again, we pick up the ratings that we had calculated above, and we just have to put it in an ordered dict where the key is the movie ID. right? And each time we find a new rating, we just push it into a list, right? And for that list, we can just sum them and divide them by the number of movies, right? So there we go. And now I can basically calculate the average rating for, I have the average rating for any movie you like. So you give me the movie ID, let's say 260, and I have the rating for Star Wars. Come on, we're doing RDBMS stuff out of plain Python. That's awesome, right? And all we're going to look at is, even for any data engine, these kind of data structures. We're not looking for anything special. We're going to just see, hey, your Spark, how do dictionaries work inside you? How do ordered dicts work inside you? How does a counter work? And things like that, right? So we're basically covered. Now that we've understood this part, everything else is easy, and you'll see in a minute. So default dict basically inserts a default value where there's a null. I'm not going to waste too much time there. And this is the last one, right? We're going to count the number of movies by genre one more time, right? So we're using the default dict in this case. So even if there's no genre available on certain lines, we get it. So like I said about calculating the same thing in Python, it can be done in multiple ways. You can have a more interesting way of doing it than I had. And so I'm really looking forward to those bits. But let's get back to our presentation, right? This was fun. This was quick. So what did we see? The first big thing we saw was eager evaluation. Python evaluates everything as soon as it finds it, right? That means I don't get the opportunity to optimize first. I just get the answer, right? So as my data sets increase, I'm going to be able to first say, I'm only looking for all the movies released in 1995. I'm not looking for everything. So I want to be able to filter my set down before I do evaluations on it. But right now with eager, everything's going to happen, right? So then Python represents two-dimensional data row-wise, right? All the data structures we saw, whatever you consider a record, will actually exist together, and then the next record, and then the next record, and so on, right? They are not contiguous, right? So just the apartment complex analogy, every value lives in a different house, and whoever's getting all the values will have to go to different houses, and we'll have to travel record by record. So if I say, get me row number 5, it will have to traverse through row number 1, 2, 3, 4, 5, and then get it, right? So slightly slow, but it's dynamic and it supports duck typing, so it's awesome, right? We saw that there's like 48 methods. Each list supports overhead. So like we had that spoiler alert, NumPy improves upon that, right? So what does NumPy do? I'm going to quickly check for questions before I move on. Oh, they are? Thank you, Moritz. I actually didn't rely on that dictionary so much, but thank you. Thank you, Jose. All right, let's move on. So NumPy uses uniform data types, so that Python overhead we had for duck typing goes away. This speeds things up, all right? So, and the second thing NumPy does at the cost of memory usage is to keep everything together. So NumPy will not say my movie title lives in one apartment and genre lives in another apartment somewhere else. No, genre lives right next to the title, right? And they know, so NumPy has two things. It knows how big a movie title is, movie ID, movie title, and genre, and it knows exactly where they are. So it doesn't have to waste time looking for that value, right? So can you see the difference between the two here? I've tried to color code the columns as well, so it's slightly easier, but I know that it's like a really dense diagram. You can look at it at leisure put up something in the discussions if I'm not able to answer your questions right now. But yeah, I'll look forward to your comments. All right, so this is interesting, right? Because now I can do a lot of things. NumPy is saying, as long as you care about your data types and don't make me care for your data types, I can give you speed and I can give you scale. NumPy also does one more thing, which is really, really old programmers here, I know at least one who I hope is in the session, will know the way data is represented in memory can be two different ways. It can be the row-oriented data or column-oriented data, right? And in this case, what NumPy is helping us do is say, hey, do you want me to put things in C order or Fortran order? Fortran order. Fortran order is basically all the values of all the columns together, then the next column and the next column. And I really like this. This was how Fortran would create the arrays. And this is what we call columnar databases today. They basically store all the values of the column together. If you're looking at Parquet, each file is basically one column, right? If you're looking at Apache Arrow, in the memory, it's going to say all the values of column 1 live together, all the values of column 2 live together, all the values of column 3 live together, and that's it, right? So this is fun because now what we can do is we can actually use fewer columns and not pay for shaving the extra data off, right? We can just say, I just need my movie IDs and I just need my genres and I don't need the titles, and that's it. It will not waste time getting me the titles. Did that make sense? So there's a typical interview question, find the max salary from employee table. So I just put it here. In this case, it's easier because an employee table may have the employee name, age, address, blood type, and then the salary designation as well. And you only need the ID and the salary column. So you're not paying for all the extra data. You don't have to load it. You don't have to read it, right? So this is really fast and memory efficient. Apache Arrow is a very new format. Well, not new. It's been in the works for ages now, but very interesting format that enables not only column-oriented representation in memory, but also allows interoperability. So you can have some data munging done in Python and then pass it to Spark. In Pandas, and then pass it to Spark, and then pass it to Data Fusion in Rust, and the data remains the same at no added cost. So you don't have to like serialize, deserialize, serialize, deserialize. It's really, really, really well done. So let's switch to the NumPy notebook really quickly. I will close this one and open the NumPy one. All right. This is the notebook, right? Not the 0 one. The 0 one's just empty. Here we go. Some extra buildings, more machinery. NumPy is cooking, right? So let's really quickly, again, open in Colab. You can just use this bit. I'll just run these things for setup purposes. I'm using version 1.262. Let's look at how NumPy is faster than Python lists. You know, how fast is NumPy? I don't know. So what I did was I just took a really big number, 10 million. And then I created a Python list. So list has 0 to 10 million minus 1 in one list, right? So that's a list of 10 million numbers. And I'm just going to say, how long does it take for me to sum that list? And then in a NumPy array, how much does it take for NumPy to sum it? That's really simple, right? When I run it, I can see that right now on my machine, NumPy is 22 times faster. That's awesome because as my data grows, I can do 22 times more processing in the same amount of time, right? So it's kind of cool. Here's another test, right? I'm going to take two lists this time and sum them, all right? Let's try this again. It's a more complex operation and it actually is faster. Why is that happening? Because we're basically able to multiply the gains that we get when we consider the type safety that NumPy is saying, and the contiguous data blocks in your memory, right? So again, typecasting rules are important in NumPy. If I give it an array of different data types, how does NumPy determine the data type, right? So there's a bunch of tests that I have put in. And you'll see that it just keeps saying Unicode string less than 11 characters is the first one. And that this one's, of course, an exception. And the third one is integer 64, right? So here I specified the data type. Here I specified the data type, but gave it the incorrect data. And here I did not specify the data type. So it's going to take the least widest data type to cover all the elements in the array. The smallest thing that covers all the elements. I don't know if that makes sense, but like it will. So let's look at the memory overhead, right? Because we have strict data types, let's see what the memory overhead is, right? So here's a really simple method. What I'm doing is I'm just picking up the number of bytes that NumPy array is consuming versus I'm using get size off here to say, here's the bytes consumed in the memory, right? And then I'm converting it into kilobytes for easier reading. And so when we run this, here we go. So that's kind of half-ish, right? 50% less memory. That's awesome. That's like for nothing. We just said, import NumPy as NP and then use NumPy array, and we get 50% of our memory back. That's pretty cool. So we talked about the contiguous sets, right? So we talked about the contiguous addressing of data. NumPy by default goes row oriented as well. You have to expressly convert it into columns. We'll do it at the end of this notebook, but I'm trying to avoid that, right? We'll cover that in a different session if we meet again. So let's quickly look at the memory addressing, right? Hopefully this will make sense. If it doesn't, we'll just quickly move on and pretend it never happened, right? So what I've done is I've created an array here. Each number is taking 32 bytes, right? And NumPy basically says, hey, from apartment 1 to apartment 2, because now they're equally sized, each step that I have to take is called a stride. All right, so what I'm trying to do is say how big is each stride, and that's got to be 16 in this case, right? So when you think about it, so later what I did was I created that array, and walked through each element, and I said, well, give me the memory address. How do you find that memory address? You basically look at the array interface. It's a private interface inside the array, right? And you can actually look at the data part here. And in fact, if you have the notebook, I welcome you to investigate this data structure more. It's really, really interesting. So, so when I look at the memory addresses, the Python ones are all over the place, right? There's like 52, 84, we don't know. But this one is the same address all the time. Why? Because it's just going to say 84 plus 16 here, plus 16 here, plus 16 here, plus 16. So it's just doing that. So you're checking out the 100th element means the base address plus 100 into 16. It's actually not a walk. Here it says, go to this element, this guy's going to point you to the next one, go to the next one, this guy's going to point you to the next one, and so on. So this one is really, really, really efficient. The cost is that we have to take care of our data types. Make sense? So let's do some problems with NumPy, and I'm like kind of interested in how we can leverage NumPy to look at our C, right? So again, how many movies were released each year? How many movies were released in 94, in 95, in 96? And a very common problem is that there's no group by available in NumPy. So before we get into it, I just want to check if there's questions. Anything else I should be attending to? No, let's look at NumPy. So here's what I did, right? Again, we've done this before. I say where my data is located, what those files are, the idiosyncrasies of my data set. Remember, there was the American president that has a comma in it. Now, when I have to load this file into NumPy, I will have to attend to it because the year is embedded in the title. So what I'll have to do is I'll have to create a list of titles, extract the year from it, and then do some sort of a group by. Right? That's the first problem. The second problem, on average, how many movies were released per year? So if, let's say, there were 200 movies released in 95, 700 in 96, 3 in 97, I'm just making arbitrary numbers. On average, across the entire data set, how many movies did we get every year? Did we get like 50 movies a year on average? What was that average, right? So the second one's simple if the first one is done, right? I hope you can see that. So, of course, we'll use regular expressions. I tried using this, but I just kept it aside. There's a very, very, very cool thing that regexes do, which is called a look around. And this one is called a positive look ahead, right? It's going to say, identify the comma for me that is followed by a double quote mark, right? So in this case, this one, right? So I don't think we'll need it. So let's just create a regular expression for the year. So it's going to say, hey, there's a parentheses. Between the parentheses, there's got to be 4 digits. And if you match this pattern, pick it up, right? So same as before, we're just going line by line. And we're dumping everything that we read into this data list, literally a list. So no NumPy stuff yet, right? And you can see that I created a movie ID. I did a title. In title, I'm actually joining, really interestingly. Actually, if you can figure this algorithm out, I promise you, it's so much fun. It just basically just circumnavigates the whole comma problem completely. And then I do the regular expression match to extract the year right here itself. And then the last part is the genres, right? So I just take it up and I say, here's my list. Each element in my list is a list, again, which is a movie ID, title, year, and genres, right? And then I basically say, hey, it's a NumPy array. And when I try to print the shapes, let me just run this and then try to run this one. It says you have 9742 movies, each one of them having 4 fields. Super interesting. Now I have, so if I want to print head, right? NumPy doesn't have a head, but we can use the same Python list format to say, it should have been the, so just give me the first 5 or the first 10 or whatever, right? Do you want to do 12? Let's do 12. Let's see if the American president got through. Ooh, we got it. And we got the year as well. And so now I define a general purpose group by. We did this in the last notebook. It shouldn't be hard. We did this with dictionaries, right? So each time I find a new movie, I'm going to create a new key in the dictionary. And each time I encounter, in this case, I'm creating a year, right? So each time I find a new year, I'm going to create a new key, and the value will be a list with all the elements that are basically belong to that key, right? So super easy. I do that. And then I build a count function on top of it, where I say, first, build me all the groups. And then for each group, just get me the length of each group. That's my count, right? So a count is super easy to do, to literally whatever, like half a dozen lines of code. And here we go. I can now tell you we have a proper group by in NumPy and pure Python. A group by from scratch. That's exactly what a database does. That's exactly what any data engine will do. You now understand how a group by works fundamentally. So when you're evaluating group by structures and pandas in the next notebook, it's not going to be that hard. And we don't care about the syntax because that's a ship question. We don't really care about it. The C is our main concern, right? So we can just look at the count for everything. There's a movie from 1908. Okay, not bad. Of course, there were more than one movies released in 1908, but our data set only has one. So let's look at all the years. This syntax just says, give me all the elements in your NumPy array, but only give me the 0th column, like the first column, right? So I do that. I see all the years, right? There's actually a none as well. And then I see the count. And that's exactly the same corresponding count. So I can actually see I have the count for every single movie released every single year in my data set. And here's the average. About 91 movies every year. Not bad. I'm not going to cover the row versus columnar. I've tried to play with it and convert the row major order to column major order and so on in memory. It gets super confusing really, really fast. So let's skip this part and move on to pandas, right? So going back to our presentation, let's just quickly summarize. Significantly faster vectorized execution. Did you understand what vectorized was? Vectorized is we don't have to write for loops, right? It applies to the entire list all at the same time. Homogeneous data types, one column, one type, period, right? Low-level implementation in C. So these are basically C-like arrays. So anybody who's programmed in C will know that that's how you count up an array in C, right? With a stride and a base address and so on. And then there's tons of helper functions for maths and numbers that we didn't touch, but there's no group by, there is no join. So what do we do for our regular data wrangling needs? We're going to have to implement them from scratch. But the pandas folks said, well, there was once a package called plier in R that had the split, apply, combine approach. Let's build that in Python and use NumPy as our data engine, right? So every column in a pandas data frame is effectively a NumPy array. And then pandas builds the group by and all of that fun stuff for you, right? The next version of pandas supports Apache Arrow as a backend. So instead of using NumPy, you can start using Apache Arrow, right? I don't want to cover Apache Arrow in this workshop, primarily because it's like a half an hour discussion on its own. And I want to show some code around it. But in the workshop, in the repo, I will be building a separate Arrow related section. So there's a curiosity note I wrote here. Let's read it later, right? Let's switch to the pandas notebook at this point. So I'm going to go pandas, quick. We have to cover Spark at least. So we'll do the basic stuff in pandas and then move on to Spark because there's interesting questions in Spark that I think you'll enjoy. Same as before, let's locate the data, let's specify the file names, import NumPy and pandas. I'm using these versions, hopefully your versions match. And then we do this CSV dialect. So now with pandas, we're going to get a helper function that reads our CSV for us. Instead of building all those tricks that we built to address the commas and so on, we're going to need this, right? So So let's try loading movies with this one. And if you were to do just a pd pandas.read CSV, it's going to break because the name they have given in this particular case is quote character, right? So really old programmers like me, we used to just use the escape character, but CSV dialects have become complex enough, thank you to Microsoft Excel, that we now have these two definitions. And so the method signature that pandas read CSV method requires is a quote character, right? In our case, it's the same thing, it's the double quote, right? The README file says it's escaped using double quotes, but in reality, it's quoted using double quotes, right? So that small semantic difference ends up crashing your code and giving you a headache for hours and hours. Just, you don't have to lose hair like I do. This is remember your code card. And that's it. So when we basically run this stuff, we can actually do we can actually really quickly look at it. And we got the American president correct this time. Not that hard. In fact, like a single line of code. Wow. Right? So I really appreciate pandas and what it brings to the table, especially when you think about that underneath it all, it's an entire NumPy column. So I can do really advanced math and just be in pandas. So here's the data types for the column. I'm going to just load the other ones as well really quickly. This shouldn't be a problem. They shouldn't be hard. I'm interested a little bit in the ratings one. So here's how I do date timestamps, all right? I just import that as regular integers and then convert them after the fact. I don't know why. Maybe it's my luck. It almost always breaks when I supply a date time directly into the schema, right? So let's do that. I have supplied a schema here, and then I have set up my quote card and everything else, and I'm going to load the file. Loads. This is an integer right now. Now I'm going to convert it using the toDateTime method, and I'm going to just run that. Here we go. Now I have a proper date time, and I can now start extracting the actual date time for my ratings instead of the Unix timestamp that we had before. Make sense? So I just created a new column, and it's literally like a Python list. So you can just keep adding new keys as new columns. Super simple. As of now, is there anybody who thinks this is really complicated code that we could not make sense of? Oh, did everybody? Oh, no, there's people here. I said, because I can see you guys, I feel like, oh, everybody's left and I'm talking into the void. Well, thank you so much. All right. So this is super simple code, right? Let's try one more time and playing with the date time, just so we remember this one. All right. This time we're going to create 3 columns, say date, month, and year, and we're just doing the same thing. It's literally the same operation, and we now can group by the month. We can say how many movies released in September, or how many ratings, I'm sorry, in this case, were given in the month of September across all the years. Not bad. Or are there more ratings given on the first of the month or on the last day of the month? Right, so we can start thinking about time series. We're not covering time series, which is a shame, but we can start looking at time series earnestly with this data. That's it. I think tag is the same thing. I'm just going to run the notebook, see if anything breaks, and then quickly move on to actual data munging, right? Yeah, this is the Zen of Python. I kind of like it. But let's move on to the second pandas notebook. Surprisingly, the pandas notebook took us like 5 minutes. Once we knew what the C looked like, Yeah, this was easy. Same thing as before. We're running everything, and then import numbers. Here's the. Let me just load the movie set and then ask questions. Right. So we have the movies in place and the ratings in place. Come on, date time. Right. Now let's do the problems. Right. Find out how many movies have commas in them. How many movie titles have commas in them? Can we again extract the year of the release? We've done this before and you know it's easy, right? And put it in a separate column. How many movies in the data set from each year? We've done this before. Super easy. Can we calculate an average rating? Again, come on. How many times was each movie rated? The rating frequency. Is there a way I can query the movie ID and get its title? So we're doing kind of the same things, but in pandas this time. Let's see how easy it is, right? So here's my movies. And I can just say movie title dot string dot contains a comma, and you give me a head of that one, right? So I have a mask. I have a data frame that's as large as the previous one, except if it doesn't contain a comma, it says false. Where it contains a comma, it says true. I can filter that and just say how many trues, right? So here I go. We can just do a dot contains equal true. That's a filter. And that we get all the movies that have only commas in them. That's a simple count, right? So suddenly my code is so much more readable. That's the thing that pandas brought to the table. It took up everything Python gives, everything NumPy gives, and gave it conveniently, right? Year of release. How hard can this one be, right? So the LOC is interesting, right? So pandas, what it does is it adds an extra data structure to your data, which it calls the index. The index is basically a NumPy array, but it's not mutable. You can't change it. And it guarantees uniqueness. So you can't have two duplicate values, or you cannot have duplicate values in an index. We have 10 minutes. I'll touch the first spark and then we'll go to questions, right? And the same, like you would have guessed it, right? We just run a regex pattern, extract the year. We've done this before. Super easy. We're just running a string method here, right? And that's it. And now we have a year in a separate column. So what took us maybe 6 lines of code before takes us 1 line of code, right? And now I can actually do the same thing. I can actually group it by year. So instead of writing a group by method, my own, pandas provides me a group by object. This is a group by object, and it will have its own set of methods. So let me just do that. Let me just first create a group by, and before I execute this, let me just show you that the group by method itself has tons of features available in it, right? And when you think about it, group by must support some sort of duck typing, right? Because you can group by on any kind of value. So you can have all these aggregation functions built into the group by, right? And just play around. Once you have a group by object, just keep playing around with it, right? So with the group by, I can look at all the groups and all the keys. Do you remember the groups and keys? We created a dictionary and we created a keys in those dictionary. That's a group by object, right? You see that? It's a dictionary inside. How many unique years in the movies? We know this answer. Come on, it's super easy now, right? So we know the C, so the ship gets easy, right? How many from each decade? Come on. Just quickly asking a question in the interest of time. Do you want me to run with the rest of it, or? Thank you, Ade. Do you want me to run with the rest of the Python pandas workshop, or can I just move on to Spark? I'm going to move on to Spark. Okay. Let me stop the old ones. Right, so I'll move on to the Spark notebook. And let's cover the first two really quickly. It's the same pattern. We've seen this before, right? Spark, because it's a Java library, and the way Spark works is that it has a central processing and task scheduling engine, which then delegates the tasks to individual machines. So if you have data that is larger than the memory of one machine, Spark can distribute it and process chunks in parallel. It's just like pandas built upon NumPy and Python. Spark built upon the basic low-level stuff that Hadoop provided, right? And it came out of, I think, Berkeley. Really successful, but you're now dealing with Java, Scala, and Python. So operationally, it's kind of complicated. But let's look at it for like 30 seconds, and you'll realize it's super, super simple because we know the C. So I'm using this library called FindSpark just to get wherever my Spark is installed in my machine, and then just quickly create a session. A lot of people ask me this question about the difference between a Spark session and a Spark context. It's kind of in the name, right? A session is an entire Spark cluster running, right? And a context is your passport to that cluster. So multiple people can use that. And so the one key that's given to you to access that resource is your context, right? So I don't know why it's not creating, but hopefully it will in due time. Yeah, Spark runs slow on my machine. Oh, here we go. We have one. All right, so let me uncomment and run this. We have Spark, and Spark gives you the Spark UI that I can open in a different tab, hopefully. Continue to HTTP. Right now, I can see all the jobs that are running, the stages that each job is at, and so on. So we'll not cover this bit. Let's just get to data munging, right? Back to our business. We have Spark running. You have all the scripts to do that. Super simple. Let's set up the schema for each of these data files, right? So we've specified the schema before in pandas, if you remember. We just have to use the struct field construct here, believe it or not, for functional programming reasons. Because we're running in Java now, we do not have the luxury of duck typing. So there you will see certain idiosyncrasies creep up into the code that you'll have to account for. But once that's over, it's just, again, just mechanics. And we get to load the movie again. There we go. So again, imagine how this data is getting created. Basically, a call is going to the Java virtual machine, which is returning this raw data. So you don't have that glossy looking Python pandas table here anymore. You basically have a plain text representation of the data, right? So it's dot show does the first 10 and so on. So there's this notion of an action in Spark. Spark is the first one that we're touching that does lazy evaluation. It still has row-oriented data representation, but it's doing lazy evaluation. It's not going to run your computation until you call one of these actions. And actions are basically a fancy way of saying, show me the results. Give me all the results. That's it, right? So we're going to just load different files here, see if it works, and that's it. It's working. So what I'm going to do is I'm going to stop this one. and move on to the actual data analysis one, and then I think we'll run out of time. I wanted to do task. It was so much fun. But, another time. And the workshop's alive on GitHub. It keeps growing. So please connect there. I think you're going to have a lot of fun. Here we go. So now we have a new Spark session. I'm going to create a new one here. Takes a minute in my machine. But we, in the meantime, can, this time was awesome. I think it knows that I'm running out of time. So this time we're looking at a beautiful set of problems here. Okay, we want to be able to clean up some data. Then we want to be able to say, list all the unique tags that I've found, sorted lexically, A before B, B before C, C before D, and so on. And then which movies have most number of tags? Which users have added most number of tags? Which users have added most number of tags? Which users have tagged most numbers of movies, right? So these are kind of like the first light bulb questions that come to you when I say, hey, there's a tags file and it's got movies and tags in it, right? So let's load the data again. This time I've just crunched everything into a single cell. It should be fast. And we have the tags data with us. So I'm going to just try the first couple of exercises. In the meantime, if you have any questions, I would request that you start putting them in the chat or in discussions, wherever you like, and then we'll start covering those up. So again, same, we're defining some regular expressions in order to be able to extract the quotation marks. And that's it. We're basically just going to filter each value and see if they're able to trap the individual quotes, right? Here we go. So first we converted everything into a lower tag just so we are able to better compare things. And then we did a distinct. It's not that hard, right? How do you do a distinct? You either do a group by or you do a distinct, and let's compare both of them, right? So let's compare. Oh, let's do this one as well. The distinct tags one was using the word distinct, the compute distinct, and then show was the action that caused the compute. Here we're using a group by and count and shows the action that causes compute, right? So let's compare the two. And if we just look at the explanations for each of these, you'll actually see that they're identical. I think I have it here. Right. So we actually have it here in for both distinct and group by. And what you'll realize is that internally they're identical. Distinct is the same as group by. Effectively, we have a dictionary and we're looking at unique keys. So even in Spark, which is a distributed whatever, it's the same thing. We just need a dictionary and a bunch of keys, right? And then we can continue on our way for cleaning up all these quote marks, right? So we have, I think we've covered. Oh, there's actually a URL with a Christmas in it. So good. I think we caught it, and we know how many movies have each tag, right? So Christmas goes to 1,100 movies. But Christmas England history goes to one movie, and Tree Dealer goes to one movie. I don't know which one this is. Interesting, right? And so now let's move on to the next question, which is which movies have most number of tags? We have 2 minutes. Awesome. And we're doing the same thing. It's basically the same group by that we have, right? And we now see that sci-fi has 658 and so on and so forth, right? So we could like basically order by. Um, let's do a joint. Let's figure out what that movie is that has so many right? That so many people have tagged sci-fi. Um, yeah, we saw this movie before, right? We saw this one in the first Notebook. Yeah, this art film went around, right? And so on and so forth. So I think we're 50% through. Let me just give you the summary notes on Spark. It is lazy, has a slightly more complex ecosystem, which makes the operations, the deployment of the clusters, the management of the clusters, data I/O, maintenance, that becomes a significant part of your strategy of using Spark, right? A significant portion of your cost will actually go there instead of actual data analysis. Um, and I've described the details of the eager evaluation versus lazy evaluation and so on here. But that's about it, right? So let me scroll all the way down. Thank you, PyData Global. You folks are all aces, and I'm open to questions. There's a question, when would you use Spark instead of Pandas? I would always go with Pandas first. Occam's razor, use a simpler one first. But obviously, Pandas grow slow, really, really fast, right? If your data grows, I think Pandas gets really slow, really fast, right? So if your compute is really slow, or if your data is larger than the memory available in your system, prefer Spark. You're going to have to fight with your IT team to get Spark running. That's kind of a cost. Or if you're on Amazon, SageMaker and Glue provide Spark managed. So there it's super easy, both on Amazon and on GCP and Azure. It's really easy to pick it up in cloud, but for physical systems or data centers, you're going to have to fight with some people, right? Is it possible we continue with Shaurya? I'd like to listen to him more. Oh, thank you so much. That's like the best comment ever. Yeah, I don't know. PyData people are gonna come to my house and beat me later. So I don't want that. This is not getting recorded, right? It is. Oh shit. Um, thank you, Kalyan. I really was hoping that you'll join the call. So thank you so much. Um, Carolina, I'm from a computer science background. I do the same thing. Thank you. Um, using pandas and Python together, analyze is a great starting point, but before settling on just this, okay. Yeah, so I don't know if we have any more questions. I don't know how to close the meeting. There was somebody else who was hosting this with me, right? Can I invite them back? I know, Gulema. Thank you so much. I know. I've done this for 5 days and I don't get bored. It's really interesting when you start looking at data. And I have situations where I then marry the IMDb data with the movie lens data set, and then we look at the bias built into the ratings, or if there is any built into the ratings, and the risk, and so on and so forth. So we quantify the movie industry. So this really helped me build the business case for releasing my film, actually. So yeah, there's a practical use here. Thank you, Minna. Thank you, Liam. Did I lose the host? I'm really stuck. What do we do next? This is PyData. Should we just continue?
Yeah, yeah. Sorry, I
Hey,
had
listen.
network once. Yes, so you didn't
Sure.
lose the host. Yep.
Okay. Right. Sorry, I didn't know what to do, and so I'm kind of lost. Let me stop sharing.
Sorry, guys.
Hey, Conrad. Thank you. I
Back.
panicked for like 30 seconds. I kind of went nuts. All right.
There is.
Thank you, Christopher. I appreciate the
Have we
Yeah.
all wrapped up? Because we're trying to start the next session.
Right. Okay. So everybody, thank you for joining, and I wish you all the best. Connect with me on GitHub or LinkedIn, and I look forward to every other session on PyData. Thank you so much.